Hello, I am Chai Victor Habi, a PhD student at Tel Aviv University. Today, I will present our paper, Learn Generative Misspecified Lower Bound. This is joint work with my supervisors, Professor Hagit Messer and Professor Yoram Bressler. We begin with a short introduction and some notations. Then we will present the Learn Generative Misspecified Lower Bound. In the experimental results, we will demonstrate its benefits using two examples. Finally, we will conclude. Let's begin with some notations. X is a random measurement vector sampled from a true distribution denoted by f of t, and it is parameterized by the vector theta. We assume a misspecified distribution denoted by f of m, which is different from the true distribution. A misspecified estimator, theta hat, is derived from the misspecified model. Now, we wish to study the misspecified estimator when the true distribution is completely unknown but a dataset of samples is available. When a statistical model differs from the true one describing the measurements it assumes, a lower bound on the estimation error of an unknown parameter is the misspecified Cramér-Rao bound, or in short, MCRB. To approximate the MCRB when the true distribution is completely unknown, we require a set of i.i.d samples from the true measurement distribution. Note that this approach requires that all vectors in the set are sampled using the same parameter value. Now, if the true parameter vector is provided alongside the set of samples, a lower bound on the MSE matrix between the misspecified estimator and the true parameter can be approximated by equation 1. This approach suffers from two limitations. 1. We cannot evaluate the MCRB at parameter values for which no sample data is available. 2. It requires the collection of a large number of samples. In this paper, we present an enhancement to the sample approximation of MCRB using learning techniques, which is inspired by the recent generative Cramér-Rao bound. We call this approach the Generative Misspecified Lower Bound, or in short, GMLB. In the rest of this presentation, we will present the GMLB and show how it overcomes the limitation of the classical MCRB. The GMLB consists of two steps. In the first step, we learn a generative model of the true distribution using the dataset dt with NV measure parameter pairs. Specifically, we use a conditional normalizing flow, or in short, CNF, with the goal of simulating the measurement process. The CNFG has two inputs, a conditioning input theta and a random input z. G itself is a deterministic function implemented as a neural network. Now, since Z is a random variable, the generative model is a random mapping from theta to gamma. We train G by maximizing the likelihood over the dataset dt, which is equivalent to minimizing the KL divergence between the generated samples and the true distribution. In the second step, we are giving the parameter vector for which we wish to approximate the bound. Then, using the CNF, we generate a set of NG measurement vector for the specific parameter vector. Finally, to obtain the approximation, we plug the newly generated set into the MCRB sample approximation. We demonstrate GMLB on two problems: a linear model with Gaussian noise, a non-linear model with truncated Gaussian noise. In both examples, the measurement matrix and covariance matrix are unknown. In the linear model, the measurement is a linear transformation of the parameter vector with an additive Gaussian noise. In the non-linear example, we add an element-wise non-linear function psi Then we truncate the measurement to obtain the true distribution for this example. For both examples, we assume the same misspecified model, a linear model with additive Gaussian noise. Using this misspecified model, we can obtain a closed-form solution for the MCRB. We compare our approach denoted by GMLB head to the sample approximation of MCRB denoted by LB head over a test set of 20 different theta values. One crucial difference between the two approaches is the required datasets. The MCRB sample approximation required 20 sets, one for each parameter value in the test set. Instead, the GMLB dataset do not contain samples with parameter values that exist in the test set. The figure below presents the trace of the analytic MCRB in solid line versus the trace of the two approximation method, GMLB in dots and MCRB in crosses. This is calculated over different parameter vectors. In the left figure, we see the results of the linear Gaussian example, whereas in the right figure, we present the results of the non-linear model. Both figures shows that the GMLB has a smaller spread than the classical MCRB. Now we present results in terms of sample complexity. To achieve this, we define the relative error over the entire test set, which is defined in the following equation. The figure below presents the relative error in the y-axis versus the number of samples on the x-axis. On the left and right figures, we see the same examples as previous slides. Both figures showed that GMLB can reduce the required sample complexity by an order of magnitude or more. We have introduced an enhancement to the classical data-driven MCRB called GMLB. GMLB enables the reduction of sample complexity and evaluation of the bound for values of the parameter that is not present in the dataset. Finally, we presented results on two examples. The code of this work is available on GitHub. A link is provided on the QR code on the left. In addition, the QR code on the right provides a link to our GCRB paper. Thank you for listening. For more details, please check our paper.